Okay, we're going to start chapter 4, and the first part of chapter 4 is all about what are called exponential functions. So till now, we were focusing on, it was all about polynomial functions, like x squared or x cubed minus x, and so on and so forth. These are all polynomial functions. And what makes them a polynomial essentially is that the variable is placed to a power. And the exponential function is just the reverse. So an exponential function is something like, say for example, f of x equals 2 to the x power. So notice the number, sort of the constant number, is on the bottom, and the variable is the exponent. So the variable is the exponent. And that's what makes it an exponential function. So for starters, what we're going to do is we're going to just graph and see some general properties of exponential functions. So we're going to graph a couple of these, and then we're going to see some type of properties, things that happen to the graph, sort of as x becomes larger and larger, and as x becomes smaller and smaller. So let's start with this particular graph. F of x is 2 to the x. What does that look like? Well, let's plot some points. So here's x, and here's f of x. Let's do, say, -2, -1, 0, 1, 2, and 3. And just to see what might happen in between with some non-integer values, let's do like a half over here as well. Okay, so if we have -2, that's 2 to the -2, which is 1 over 2 squared, which is, sorry, not 4, but 1/4. 1/4. Then we have 2 to the -1, which is a half. 2 to the 0, that's 1. 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. And remember that 2 to like the half power, that's the square root of 2. And that's approximately like 1.4. Okay, so what we're going to do here is we're going to take these points and we're going to plot them in the xy plane. And what we want to do now is to see what happens as x goes to infinity. So 1, 2, 0, -1, -2, 3, and 1, 2, 3, 4. Let's extend this a little longer. 5, 6, 7, 8, something like that. And what we're going to do now is plot all of these points. So 0 goes, let me plot these with a different color. 0 goes to 1, 1 goes to 2. We have -1 here, we get a half. -2, we get a fourth. At 2, we're at 4, so 1, 2, 3, 4, somewhere here. At 3, so this is 3, 2, 1, -1, -2. Here's 4, here's 8, so we have 3, 8, something like this. So notice that this graph is growing really fast. Of course, at a half here, we're at square root of 2, which is, somewhere over here. So here's a half, and here's a square root of 2. So what we get is this function that grows, what's called grows exponentially. So it sort of starts off really small, and then as time goes along, or as x becomes larger, this grows really, really, really fast. And that's why you might have heard the term exponential growth. It's because these functions grow really fast. That's why the terminology is there. So let's just state that. So note here that as x grows, as x goes to positive infinity, the y values also go to positive infinity because it's growing and growing and growing as y grows. And as x becomes smaller and smaller and smaller, notice that these values are getting closer and closer to 0. So the y values actually go to 0. They never touch 0, but they get closer and closer. So it actually turns out that the x-axis is actually an asymptote. It's something where as x goes to negative infinity, y goes to a particular value, but never actually kind of attains it. So this is actually a horizontal asymptote. So I'll state that separately down here. So the line y equals 0, which is the x-axis, is a horizontal asymptote of the function 2 to the x. Okay, so this is one example of an exponential function. We're going to do one more example, and then we'll leave you with some exercises here. So let's consider f of x, or let's call it g of x, which is 2 to the minus x. By the way here, I forgot to mention, so the domain of f is all real numbers. You can plug in any number you like. And the range, you get every value above 0. So it's actually 0 to infinity, but not including 0. These are some important properties here. Let's now look at the function 2 to the minus x. Notice here, by the way, this is the same as 1 over 2 to the x, which is also the same as 1/2 to the x power. Okay. Now, why is it the same as 1/2 to the x power? Because 1 to the x is equal to 1 for any x. Okay. So it's essentially still it's an exponential type function where the base point, so in general, before I do this particular problem, in general, an exponential function is of the form f of x equals a to the x, where a is a number. A is, and usually a positive number. Maybe some other time I'll tell you why we don't usually use negative numbers there, but for now we're just going to assume a is a positive. So here, for example, we have a to the x, where a is 1/2. Okay. We'll do this in two ways. Note that g of x is actually just a transformation of f of x. G of x is a transformation of the original function we started with, which was 2 to the x. How is it a transformation? We replaced x with minus x. And remember, when we replace x with minus x, it just flips the graph across the y-axis. Okay, so that's hopefully something we recall from one of the previous chapters, but let's do it from scratch. Let's just, and we'll see that it actually is exactly what we said. It's the flip of the other graph. Let's plot some values of x. Let's do negative 2, negative 1, 0, 1, and 2, and that'll give us the general feeling. So at negative 2, we have 2 to the minus 2, which is 2 squared, which is 4. Here we'll get 2 to the minus minus 1, which is 2 to the positive 1, or 2. 2 to the 0 is 1. Here we have 2 to the minus 1, so we have a half. Here we have 2 to the minus 2, which is a fourth. So what we end up with is the following. So we have negative 1, negative 2, 0, 1, and 2. 1, 2, 3, 4, 5. So at negative 2, let's plot again with red here. We're going to do 4. Negative 1 maps up to 2. 0 maps to 1. 1 maps to a half. 2 maps to a fourth. And you can see that you're going to get exactly the flip of the other one. So the original one, f of x, looked like this. This was f of x. And g of x, this is 2 to the minus x. Oops. This is 2 to the minus x. So you can see there are exactly flips across the y-axis. And here again, so the domain of g is still all real numbers. The range of g is still everything above 0. But now, for g, as x goes to positive infinity, y goes to 0. And as x goes to negative infinity, y goes to positive infinity. So the long-term behavior just flips. Okay, so let me leave you here with a couple of exercises. So graph. Oh, and of course, before I label the exercises here, still the y equals 0 is a horizontal asymptote. So we have horizontal asymptote at y equals 0. Okay, so exercise here, so go ahead and graph a couple of functions. So one, y equals 3 to the x. Go ahead and graph y equals 3 to the minus x. And then let's graph y equals 3 to the x minus 1, and then plus 1. Okay, so these are all these two are very similar to the ones that we just did, except with the base 3. This one is just you can use some shifts, and that should get you what you want. You want a graph, and again, label any horizontal asymptotes, and also go ahead and find the domain and the range for all of these. Okay, we will stop here for now, and we will continue this in the next video.